Hello, I'm so glad you're here. Maybe you've had a long day. Maybe thoughts are swirling in your mind, keeping you from rest. But right now, you don't need to resist any of that. Just allow yourself to relax. Let this time belong only to you. You don't have to do anything. No need to rush anywhere. All you need to do is listen calmly and breathe. The world can wait. And together, we'll set out quietly and carefully on a journey to a place most people rarely pause to consider in their daily rush. Tonight, we're going to talk about our true cosmic home, the solar system. This isn't just a collection of distant objects in the sky. It's a neighborhood of worlds where we live, though we rarely think about it. If these gentle explorations help you unwind, consider supporting this channel with a like and subscription. It helps others find their way here too, one peaceful soul at a time. Now, let's begin. Neptune's winds exceed the speed of sound. Despite being the farthest known planet from the Sun, Neptune has the fastest winds in the solar system. These winds tear through its upper atmosphere at speeds exceeding 2,000 kilometers per hour. Faster than the speed of sound on Earth. That's roughly 5 times faster than a commercial airliner. These winds are likely powered by the planet's internal heat, which continues radiating outward despite the frigid conditions at its surface. Neptune's atmosphere consists primarily of hydrogen, helium, and methane, and the winds carve massive storm systems into the planet's pale blue clouds. It's an icy world in constant supersonic motion. Mars has a continent-sized canyon, stretching more than 4,000 kilometers along the Martian equator. Valles Marineris is the largest canyon system in the solar system. It would span the entire width of the continental United States. In places, it plunges more than 7 kilometers deep, more than 5 times deeper than the Grand Canyon. Scientists believe it formed through a combination of tectonic stretching, volcanic activity, and erosion. Unlike Earth's canyons, which are typically carved by rivers, these rifts may have opened when the planet's crust cracked and stretched. It's a scar on Mars' surface, hinting at a turbulent geological past now frozen in time. Venus has no magnetic field. Despite its similar size, mass, and composition to Earth, Venus lacks one crucial planetary feature: a global magnetic field. Earth's magnetic shield is generated by the motion of molten iron in its outer core, protecting the planet from solar radiation. Venus, however, likely has a sluggish or even solid core, which may prevent the dynamo effect needed to create a field. Without this protection, Venus's atmosphere is constantly bombarded by the solar wind, which has stripped away lighter elements over time. The absence of a magnetic field helps explain why Venus, possibly once similar to Earth, became a hellish world. On Uranus and Neptune, it may rain diamonds. Deep within the atmospheres of Uranus and Neptune, conditions may be so extreme they can create something exceptional: falling diamonds. These ice giants have thick layers of methane gases. Under enormous pressure and high temperature, scientists believe methane can break apart, releasing carbon atoms. These carbon atoms then compress into crystalline structures, forming tiny diamonds that rain down toward the core. Laboratory experiments have recreated this process, showing how hydrocarbons can condense into diamond under the right conditions. If this theory is correct, storms of glittering crystals may drift through the deep blue darkness of distant gas giants. Earth is the only planet with plate tectonics. One of Earth's most distinctive and life-sustaining features is its system of plate tectonics, a dynamic network of moving crustal plates floating above the mantle. These moving plates cause earthquakes, build mountains, and recycle carbon dioxide, regulating climate over geological timescales. To date, no other planet demonstrates clear evidence of this process. Mars and Venus have surface fractures and volcanic structures, but compared to Earth, they appear geologically frozen. Earth's plate tectonics may be part of what makes it habitable, driving long-term cycles that stabilize temperature, maintain oceans, and enable continental drift over eons. Some asteroids have their own moons, though we often imagine asteroids as solitary wanderers. Some of them actually have moons, smaller bodies orbiting around them. These tiny satellites are typically captured fragments or co-formed companions. The first discovered asteroid moon was Dactyl, orbiting asteroid Ida, detected by the Galileo spacecraft in 1993. Since then, dozens of other asteroid moon systems have been found, including some with multiple moons or strange binary configurations where two asteroids orbit each other. These miniature systems show that even in the vastness of space, gravity can unite the smallest objects in quiet drifting partnerships. Mercury has a ghostly exosphere instead of a true atmosphere. Unlike Earth, Mercury doesn't have a thick atmosphere to trap heat or scatter light. Instead, it has a thin, rarefied shell of particles known as an exosphere, nearly a vacuum, where atoms bounce without colliding. This exosphere consists of atoms knocked off the surface by solar wind and micrometeorite impacts, including sodium, potassium, and oxygen. Because Mercury lacks sufficient gravity to hold a true atmosphere, these particles constantly escape into space and are replenished from the surface. The result is a ghostly, shimmering shell of scattered atoms, invisible to the eye but detectable with the right instruments. The Sun loses millions of tons of mass every second. Every second, the Sun converts over 4 million tons of its own mass into energy through nuclear fusion. In its core, hydrogen atoms fuse into helium, releasing light and heat that power our solar system. This energy radiates in all directions, warming the planets, driving winds, and sustaining life on Earth. Though the loss is minuscule compared to the Sun's total mass, over billions of years, it accumulates. Eventually, the Sun will exhaust its hydrogen supply and begin to change. But for now, it continues burning steadily, sacrificing a tiny fraction of itself every second. Saturn's rings are slowly disappearing. The beautiful rings encircling Saturn aren't permanent. They're gradually falling onto the planet, pulled by gravity and drawn down by Saturn's magnetic field. This process, known as ring rain, involves streams of icy particles and charged material drifting inward over time. Observations from the Cassini spacecraft suggest the rings may be less than 100 million years old, young by planetary standards, and they could vanish completely in another few 100 million years. Though they seem timeless, Saturn's rings are a temporary decoration, a shimmering spectacle that will one day fade from memory. Mars experiences planet-scale dust storms. Mars is famous for its rusty desert landscape and colossal dust storms that sometimes engulf the entire planet. Such storms can last weeks or even months, blocking sunlight and reshaping the surface. The dust is extremely fine and can remain suspended in the atmosphere, creating a hazy, reddish glow. Some storms start as small gusts but can rapidly grow through feedback loops between heat, wind, and topography. In 2018, one such storm led to the end of the Opportunity rover's mission, as its solar panels were choked with dust. Even without rain or oceans, Mars remains an active and restless world. Europa may have a salty ocean beneath its ice. Beneath the frozen shell of Jupiter's moon Europa, there's compelling evidence for a vast subsurface ocean of liquid water. Tidal forces from Jupiter's gravity flex Europa's interior, generating heat that may keep the ocean from freezing solid. The surface is crisscrossed with dark lines and ridges, signs of shifting ice, and spacecraft have detected magnetic signatures and chemical traces supporting the ocean hypothesis. What makes Europa especially exciting is the possibility that this hidden sea could harbor life. It's a dark, alien ocean, warmed from below, sealed by ice, but potentially rich in ingredients for biology. Mars has a volcano taller than Everest. Olympus Mons, the tallest volcano in the solar system, rises almost 22 kilometers above the Martian plains, nearly 3 times the height of Mount Everest. It's so wide it would cover the entire state of New Mexico. Formed by repeated eruptions over millions of years, Olympus Mons grew so massive, partly because Mars lacks plate tectonics. On Earth, volcanic hotspots shift over time, forming chains of islands like Hawaii. But on Mars, the crust remains stationary, allowing magma to erupt in the same spot again and again. The result is one giant shield volcano, silently towering in the Martian night. Saturn's rings are as thin as paper. Saturn's magnificent rings stretch more than 280,000 kilometers across, yet they're astonishingly thin. In most places, their thickness is less than 100 meters. That's thinner than many city buildings. Made predominantly of water ice, ring particles range in size from dust grains to house-sized boulders. When sunlight passes through the plane of the rings, they nearly vanish from view, like a pane of glass turned edge-on. Their flatness is maintained by the planet's gravity, self-organization of billions of icy fragments, and the influence of small shepherd moons. From afar, they appear solid, but up close, delicate and ephemeral. Earth is the densest planet. Of all the planets in the solar system, Earth has the highest average density. This means it packs more mass into every cubic centimeter thanks to its composition, a metal-rich core and silicate mantle. Earth's density is about 5.5 grams per cubic centimeter, higher than Jupiter's, despite the gas giant's much larger size. This high density plays a key role in generating Earth's magnetic field, which arises from the motion of molten iron in its outer core. Our planet's internal structure, compact, heavy, and layered, shapes not only its gravity, but also its geology and protection from space. The sun vibrates like a musical instrument. Though we can't hear it with our ears, the sun constantly rings with pressure waves running through its blazing layers. These oscillations, caused by rising and falling currents of plasma, generate ultra-low frequencies far beyond human hearing. Scientists study these vibrations through helioseismology. By tracking how waves travel and reflect inside the sun's body, researchers can map its internal structure, similar to how geologists use seismic waves to probe Earth's interior. These solar songs reveal hidden currents, magnetic activity, and fusion dynamics deep in the core. In a sense, the sun is always humming, quietly revealing its secrets through vibration and rhythm. Venus rotates backward. Unlike most planets in the solar system, Venus rotates in the opposite direction, a phenomenon known as retrograde rotation. On Venus, the sun rises in the west and sets in the east. Even stranger, its rotation is extremely slow. One day on Venus lasts longer than its year. It takes 243 Earth days to complete one rotation around its axis. Scientists aren't sure why this happened. But one possibility is a giant collision early in its history that altered its spin. Another theory suggests tidal interactions with the Sun slowly flipped its axis over time. Whatever the reason, Venus stands out as a slowly rotating world with an inverted rhythm. Jupiter has over 90 moons. The gas giant Jupiter isn't just the largest planet, it's also the king of moons. Currently, astronomers have identified over 90 natural satellites orbiting it, and new ones are still being discovered. Its four largest moons, Io, Europa, Ganymede, and Callisto, are known as the Galilean moons, named after Galileo Galilei, who first observed them in 1610. But beyond these giants, there's a swarm of smaller, irregular moons, many captured from passing objects. Some orbit in reverse, some are just a few kilometers across. Together, they form a miniature solar system in orbit around Jupiter, bound by the planet's gravity and its history. Mercury hides ice in its shadows, scorching hot by day and freezing by night. Mercury isn't the place you'd expect to find ice. Yet it's there. At its poles, deep inside craters that never receive sunlight, temperatures remain low enough for water ice to exist. These permanently shadowed regions act as natural freezers, preserving ice for millions of years. Radar reflections from spacecraft like Messenger confirmed the Rom comet impacts, or ancient volcanic outgassing. In the heart of one of the hottest planets, ice survives, locked in darkness, protected by crater walls from the relentless solar heat. Pluto's heart may hide an ocean. The bright heart-shaped region on Pluto, known as Sputnik Planitia, isn't just a picturesque landscape. It may be the surface manifestation of a massive underground ocean. Though Pluto is far from the Sun and cold enough for nitrogen to freeze, data from the New Horizons spacecraft suggests a layer of liquid water may lie beneath its icy crust. The weight of this giant basin and visible geological activity hint at a viscous, convective subsurface layer. If this ocean exists, it may be kept liquid by heat from radioactive decay and insulating layers of ice above it. Even in the frozen reaches beyond Neptune, a hidden sea may quietly exist. The asteroid belt is mostly empty space. Despite popular depictions, flying through the asteroid belt isn't like dodging rocks in science fiction. In reality, the belt is vast and sparse. Located between Mars and Jupiter, it contains millions of rocky bodies, but they're separated by enormous distances. A spacecraft passing through would almost never encounter an obstacle. The total mass of the asteroid belt is less than 5% of the Moon's mass. Its largest members, like Ceres and Vesta, account for most of this mass. The rest are scattered fragments of the early solar system, ancient building blocks that never assembled into a planet. Uranus rolls around the Sun. Most planets spin like tops, slightly tilted on their axis. But Uranus is tilted so much that it essentially rolls along its orbit with an axial tilt of 98 degrees. This means its poles during part of its orbit point almost directly at the Sun, granting extreme and bizarre seasons. Each pole experiences 42 years of daylight, then 42 years of darkness. The reason for this tilt is still debated, but the planet was likely knocked on its side by a giant collision. Uranus's tilt gives it one of the strangest climates in the solar system. Jupiter's radiation belts are deadly. Jupiter is surrounded by a gigantic magnetic field, the strongest of any planet, and within it are radiation belts of such intensity they would destroy an unshielded spacecraft within hours. These belts are filled with charged particles trapped by the planet's magnetic field. forming zones of high-energy radiation similar to Earth's Van Allen belts, but far more powerful. Jupiter's largest moons also experience this radiation, which can affect their surfaces and potential habitability. To survive in Jupiter's orbit, spacecraft need special shielding or low radiation trajectories. It's a beautiful world, but wrapped in invisible danger. The Sun contains almost all the solar system's mass. At the center of our system, the Sun dominates not only in light and gravity, but in sheer mass. It holds over 99.8% of all mass in the solar system. This means everything else, all the planets, moons, asteroids, comets, and dust, accounts for less than 1/4%. Its gravitational force keeps everything in orbit, from tiny grains in the asteroid belt to distant comets in the Oort cloud. It's this colossal mass that fuels the fusion reactions in the core, converting hydrogen into helium and flooding space with the energy of day. There are more dwarf planets than classical ones. Beyond Neptune lies a scattered population of icy, distant objects, many large enough to qualify as dwarf planets. Pluto is the most famous, but it's just one of many. Others like Eris, Haumea, and Makemake share this status, and new candidates are constantly being discovered in the Kuiper Belt and beyond. In fact, the number of dwarf planets may vastly exceed the number of 8 classical planets. These small rounded worlds are relics of the early solar system, untouched and ancient. Though they orbit in cold shadows, they preserve clues to the formation of everything we know. One day on Venus is longer than its year. Venus has one of the slowest rotations among planets. It takes 243 Earth days to rotate once around its axis. Meanwhile, it takes only 225 days to complete one orbit around the Sun. This means one day on Venus, from one sunrise to the next, is actually longer than a full year. This slow rotation also contributes to extreme surface conditions, with temperatures high enough to melt lead. Combined with its dense, acidic atmosphere and crushing pressure, Venus is a world of slow, boiling heat and eerily sunless days. Titan has lakes of methane. Saturn's largest moon, Titan, is the only other place in the solar system where stable liquids are known on the surface. But it's not water. Instead, Titan's lakes and rivers consist of liquid methane and ethane, flowing across a landscape shaped by cold chemistry. Its thick, nitrogen-rich atmosphere forms weather systems with methane rain and even seasonal storms. Some of Titan's lakes are huge, stretching hundreds of kilometers. Beneath the icy surface, scientists believe there may also be a subsurface ocean of water. Titan is a world with familiar forms: clouds, rivers, shorelines, but built from alien substances. Mars moons may be captured asteroids. Mars has 2 tiny, irregularly shaped moons, Phobos and Deimos. They look more like asteroids than traditional moons. Irregular, rocky, pockmarked with craters. Many scientists believe they were once part of the asteroid belt and were captured by Mars' gravity long ago. Their strange orbits and low densities support this idea, though some alternative theories suggest they may have formed from debris after a giant impact. Phobos is slowly spiraling down toward Mars and will eventually break apart or crash into the planet. Deimos is drifting away. These little moons are quiet passengers in orbit, remnants of a chaotic past. Jupiter glows with its own heat. Unlike most planets, Jupiter radiates more energy than it receives from the Sun. This internal glow comes from residual heat from its formation. Gravitational energy released when the planet's colossal mass compressed together. Over time, it continues to slowly contract, generating heat in the process. This heat drives Jupiter's turbulent weather systems, including giant storms and swirling bands. In infrared, Jupiter glows brightly, like smoldering coals, beneath layers of clouds. It's not a star, but it almost became one. If it was slightly more massive, it might have ignited as a failed star. Neptune was discovered through mathematics. Unlike other planets, Neptune wasn't discovered simply by looking through a telescope. Instead, astronomers noticed irregularities in Uranus's orbit, tiny deviations that couldn't be explained by known gravity. Two mathematicians, working independently in the 1840s, used these strange motions to predict the location of a hidden planet. When astronomers pointed telescopes at the calculated position, Neptune was there. It was a triumphant victory for celestial mechanics, confirming that invisible forces could be detected through calculations alone. Neptune became the first planet found on paper before being seen through glass, a world discovered by numbers. Saturn's North Pole has a hexagon. At Saturn's North Pole spins a massive cloud structure in the shape of a nearly perfect hexagon. This hexagonal jet stream stretches more than 30,000 kilometers wide, wider than Earth, and has persisted for decades, possibly centuries. Scientists believe the hexagon forms through the way Saturn's atmosphere rotates and interacts with standing waves of air locked around the pole. In laboratory experiments, similar shapes appear when rotating fluids at different speeds. That such a geometric figure can naturally arise in a planetary atmosphere remains one of the most surreal and elegant phenomena in the solar system. The Sun's atmosphere is hotter than its surface. It might seem intuitive that the hottest part of the Sun is its surface, but it's not. The visible surface, or photosphere, has a temperature around 5,500 degrees Celsius. However, the outer atmosphere, known as the corona, can reach over 1 million degrees. This unexpected temperature increase has puzzled scientists for decades. One theory suggests magnetic waves from deep within the Sun carry energy upwards and heat the corona from below. Another possibility is tiny solar flares, called nanoflares. Either way, the Sun's outer layers glow with mysterious scorching heat far exceeding the source. The Kuiper Belt is full of icy worlds. Beyond Neptune lies a broad ring-like region of icy objects known as the Kuiper Belt. It stretches billions of kilometers from the Sun and is home to a multitude of frozen bodies, including Pluto, Eris, Haumea, and Makemake. These aren't stars or planets, but ancient remnants of solar system formation. Some are spherical and classified as dwarf planets, while others are irregularly shaped and tumble through space. The Kuiper Belt is similar in structure to the asteroid belt, but much colder and contains more primordial ice. It's a fossil zone, a frozen archive of the materials from which outer worlds were built. The Oort cloud may stretch a light year from the Sun. Far beyond the Kuiper Belt, even past Pluto's farthest reaches, lies a hypothetical shell of icy objects known as the Oort cloud. Though never directly observed, this colossal sphere of frozen debris is believed to surround the solar system and stretch nearly a light year from us. It's likely the source of long-period comets that appear from deep space with unpredictable orbits. These distant objects are only loosely tethered to the Sun, and a passing star or galactic tidal force can send one inward. If the Oort cloud exists, it marks the true edge of the Sun's gravitational influence, a distant halo of icy wanderers. Io is the most volcanically active world in the solar system. Jupiter's moon Io is a seething, restless world covered with active volcanoes. Its surface is constantly reshaped by eruptions of molten sulfur and rock, painting the landscape in bright yellows, reds, and blacks. Some volcanic plumes rise hundreds of kilometers into space. This extreme activity is caused by tidal heating. Io is squeezed and stretched by Jupiter's gravity, along with gravitational tugs from neighboring moons. Friction from this constant deformation heats the interior, fueling its frenzied fire breathing. Unlike Earth's cooled crust, Io's surface is young, changeable, and eternally shifting. A lava moon with a molten heart. Triton orbits Neptune backward. Neptune's largest moon, Triton, is unique among large moons in that it orbits the planet in the opposite direction of its rotation, a retrograde orbit. This backward path suggests Triton didn't form alongside Neptune, but was likely captured from the Kuiper Belt long ago. This capture could have caused dramatic upheavals, potentially destroying Neptune's original moon system. Triton is also geologically active. It has cryovolcanoes that eject icy material into space and a thin atmosphere that breathes with the seasons. Cold, distant, and moving in reverse, Triton is a world that breaks expectations at every turn. Earth's moon is unusually large. Compared to the size of its planet, Earth's moon is enormous. No other rocky planet in the solar system has such a relatively large satellite. In fact, the moon's diameter is about 1/4 of Earth's, a ratio more typical of dwarf planet systems with moons than full-sized planets. Most scientists believe the moon formed after a Mars-sized object collided with young Earth, ejecting debris into orbit that later coalesced into the moon. This close partnership has deeply influenced Earth's tides, climate, and stability over billions of years. Our moon isn't just a satellite. It's a cosmic legacy of planetary collision and renewal. Planetary orbits aren't perfect circles. Though we often imagine planets moving in perfectly circular paths around the Sun, their orbits are actually elliptical, slightly stretched circles where the Sun is offset from center. This shape means each planet has a point of closest approach to the Sun, perihelion, and a point of farthest distance, aphelion. For most planets, the difference is slight, but for others like Mercury and Pluto, it's more pronounced. These variations affect seasons, solar radiation, and orbital speed. The elliptical nature of planetary motion was first described by Johannes Kepler in the 17th century, revolutionizing our understanding of the solar system's elegant mechanics. Some comets come from the edge of interstellar space. Long-period comets, those that appear only once every thousands of years, likely come from the Oort cloud, a distant shell of icy debris that may stretch nearly a light year from the Sun. These comets move in elongated, loosely bound orbits and are often nudged from their places by passing stars or galactic tides. When they fall inward toward the Sun, they can flare into spectacular tails visible even from Earth. Some may have spent billions of years drifting in darkness before being pushed into flight. Their bright returns are fleeting glimpses of the solar system's oldest, untouched matter. The Sun will become a white dwarf. The Sun, like all stars, has a finite life cycle. In roughly 5 billion years, it will exhaust the hydrogen in its core and expand into a red giant, swallowing the inner planets. After shedding its outer layers into a glowing shell of gas known as a planetary nebula, the core will remain, a white dwarf, a dense object the size of Earth composed mainly of carbon and oxygen. This white dwarf will no longer produce energy, but will slowly cool over trillions of years. This will be the final form of our Sun, a glowing ember in the darkness, marking the end of its stellar journey. Mars has seasons similar to Earth's. Though colder and with a thinner atmosphere, Mars experiences seasons similar to ours. The reason is a similar axial tilt, around 25 degrees, compared to Earth's 23. As it orbits the Sun, this tilt causes sunlight to fall differently on different hemispheres at different times of year. The result is a cycle of spring, summer, fall, and winter, with variations in temperature and illumination. Martian seasons also affect polar ice caps, dust storms, and even subtle changes in atmospheric pressure. They unfold more slowly than on Earth because a Martian year is nearly twice as long. Ganymede is the largest moon in the solar system. Jupiter's moon, Ganymede, is the largest natural satellite in the solar system, bigger even than the planet Mercury. With a diameter of over 5,000 kilometers, Ganymede has a rocky core, a possible subsurface ocean, and a crust covered with wrinkled ice and ancient scars. Uniquely, it's the only known moon that has its own magnetic field, creating shimmering auroras in its thin atmosphere. Scientists believe Ganymede may have multiple layers of oceans interspersed with ice sheets, forming a complex inner world. Despite its size and richness, it remains quiet and dark, orbiting deep within Jupiter's magnetic embrace. Pluto is sometimes closer to the Sun than Neptune. Though typically Pluto is the most distant of the classical or dwarf planets, its orbit is highly elliptical, so sometimes it travels closer to the Sun than Neptune. This last happened between 1979 and 1999, when Pluto was temporarily the 8th planet from the Sun, not the 9th. However, these two worlds never collide or come dangerously close because their orbits are in resonance. For every 3 orbits of Neptune, Pluto completes exactly 2. This gravitational choreography keeps them in a stable dance, preventing their paths from crossing. The Sun flips its magnetic field every 11 years. Approximately every 11 Earth years, the Sun's magnetic field reincarnates. The north and south magnetic poles swap places. This process, known as the solar magnetic cycle, is linked to the Sun's internal dynamics and affects activity, including spots, flares, and coronal mass ejections. At the cycle's peak, called solar maximum, the Sun is more active with more intense radiation and magnetic storms. When the cycle declines, activity decreases, eventually reaching solar minimum. These cycles affect Earth's upper atmosphere, satellites, and even auroras. The Sun's magnetism isn't fixed. It pulses and flows like breath, a magnetic heartbeat. Planetary alignments don't cause natural disasters. A common myth is that planetary alignments can trigger earthquakes, floods, or other major calamities on Earth. But there's no scientific evidence for such effects. The gravitational pull of other planets on Earth is minuscule compared to the Moon or Sun. Even during rare alignments, their combined influence is negligible. The Moon, being close, has much greater effect on tides and tectonic stresses than massive but distant Jupiter or Saturn. Planetary alignments are beautiful and mathematically interesting, but gravitationally safe. It's a quiet dance of distant worlds, not a celestial omen. Leaving the solar system takes decades. Breaking free from the Sun's grip isn't an easy task. Spacecraft like Voyager 1 and Voyager 2, launched in the 1970s, only recently entered interstellar space, the region beyond the heliopause where the sun's influence yields to the interstellar medium. These missions took over 40 years to reach this boundary, moving outwards at speeds exceeding 60,000 kilometers per hour. The Voyagers crossed planetary orbits, passed through the Kuiper Belt, and continued into darkness. They carry still functioning instruments, plus a Golda. Earth's magnetic field protects us from cosmic radiation. Earth is surrounded by an invisible magnetic field generated by the motion of molten iron in the outer core. This field deflects charged particles from the sun, protecting the atmosphere and surface from harmful solar and cosmic radiation. Without it, the solar wind would gradually strip away our atmosphere, as likely happened on Mars. The field also directs some particles toward the poles, where they interact with atmospheric gases and form auroras, shimmering curtains of green, red, and violet light. Earth's magnetosphere is a dynamic shield, vital for preserving both life and climate over geological timescales. The Moon is slowly drifting away from Earth. Every year, the Moon moves about 3.8 centimeters farther away. This slow retreat is caused by tidal interactions. The gravitational pull between Earth and the Moon creates tidal bulges in our oceans, which in turn slightly push the Moon outward. In the distant past, the Moon was much closer and appeared much larger in the sky. As it drifts away, our days gradually lengthen, and eclipses become less frequent and less dramatic. Billions of years from now, the Moon's orbit will be so wide that total solar eclipses will no longer be possible. The sky is changing, even if we don't yet feel it. The Kuiper Belt has icy worlds with mirror-like surfaces. Far beyond Neptune, the Kuiper Belt contains not only dwarf planets, but smaller icy bodies with strikingly bright surfaces. One example is Haumea, a rapidly rotating, football-shaped object covered in crystalline water ice. Another is Eris. It reflects nearly all falling light, making it one of the most reflective bodies in the solar system, brighter than fresh snow. These objects may have been resurfaced by cryovolcanism, impacts, or chemical interactions. In the darkness at the edge of solar illumination, some distant worlds gleam like cold mirrors, catching pale light in their icy stillness. Enceladus shoots water into space. Saturn's tiny moon, Enceladus, is small but hides an astonishing secret. From its south pole burst giant geysers of water vapor and ice, crystals through cracks known as tiger stripes. These plumes are fed by tidal heating beneath the surface, where friction caused by Saturn's gravitational pull keeps a subsurface ocean liquid. Material in the plumes contains organic compounds, salts, and even signs of hydrothermal activity, raising the exciting possibility of life. Some of the water escapes into space and helps replenish Saturn's E-ring, creating a living connection between Moon and planet. Some asteroids are just piles of rubble. Not all asteroids are solid rock. Many are loose assemblages of pebbles, gravel, and dust held together only by their own gravity. Structures known as rubble piles. Such fragile bodies may form after collisions that shatter larger asteroids, with debris reassembling over time. Rubble pile asteroids can have large internal voids, spin strangely, and change shape under stress. The Hayabusa 2 and OSIRIS-REx missions visited such bodies, confirming their delicate, porous nature. They're not monolithic relics, but chaotic assemblages, ancient drifting ruins of early planet building, barely held together, spinning around the sun. Mercury's core is disproportionately large. Mercury is a small planet, but has an unusually massive iron core. This metal heart accounts for about 80% of the planet's radius, a much larger fraction than Earth or Venus. The reason for this oversized core is unclear. Some scientists think Mercury once had a thick, rocky mantle that was stripped away by a giant impact. Others believe it formed close to the Sun, where solar conditions favored accumulation of heavier elements. The result is a planet with a thin crust, enormous core, and weak magnetic field, a metal-heavy survivor from the turbulent youth of the solar system. Venus has no moons at all. Among rocky planets, only Mercury and Venus have no natural satellites. For Mercury, this can be explained by proximity to the Sun, but Venus's situation is more mysterious. It's roughly the same size as Earth, which has a large moon, yet it has none. Some theories suggest it once had a moon that fell back onto the planet or was lost in a collision. Others point to Venus's slow retrograde rotation as potentially preventing stable orbits from forming. Whatever the reason, Venus orbits alone, a bright world wrapped in clouds without a lunar companion in its twilight sky. Hubble has photographed planets from Earth orbit, though the Hubble Space Telescope orbits just slightly above Earth. It has captured detailed images of the outer planets, cloud bands on Jupiter, storms on Neptune, and seasonal changes on Mars. These images provide long-term observations that complement spacecraft flybys and offer views of evolving weather patterns, ring systems, and planetary auroras. Hubble's clarity allows scientists to track storm development, monitor impact events, and study atmospheres in ultraviolet and visible light. From its quiet perch in low Earth orbit, Hubble gazes not only at distant galaxies, but also at the changing faces of our neighboring worlds. Jupiter's Great Red Spot has existed for centuries. This giant storm swirling in Jupiter's southern hemisphere is large enough to swallow 2 or even 3 Earths. It's been churning for at least 350 years, possibly much longer. It was first observed in the 17th century through early telescopes. Over time, the storm has changed, gradually shrinking in size but remaining powerful. Its reddish hue may be caused by complex chemical reactions in Jupiter's atmosphere induced by sunlight and high-altitude compounds. Wind speeds along the edges exceed 400 kilometers per hour. While Earth storms last days or weeks, this Jovian tempest has endured centuries, trapped in the planet's turbulent belts. Neptune radiates more heat than it receives from the Sun. Though it's located far from the Sun, Neptune isn't a frozen, inert world. In fact, it radiates approximately 2.6 times more energy than it receives. This internal heat fuels powerful winds and storm systems, including the fastest winds known in the solar system. The exact source of Neptune's heat remains unclear, but possible explanations include residual energy from formation, slow gravitational contraction, or radioactive decay in its core. Despite extreme remoteness, Neptune is a world of surprising energy, cold outside and warm inside, ceaselessly churning its windy atmosphere. Earth is the only planet where water naturally exists in 3 states. On our planet, water is naturally present on the surface as solid, liquid, and gaseous states. Ice caps and glaciers, oceans and lakes, clouds and water vapor all coexist and cycle between atmosphere, land, and sea. This balance is critical for life and is regulated by Earth's distance from the Sun, atmospheric pressure, and relative climate stability. Other worlds may have water in separate forms, icy crusts, vapor in thin atmospheres, or hidden subsurface oceans, but none demonstrate the same dynamic planet-wide presence. On Earth, water flows, freezes, and evaporates in an endless, life-giving dance. The heliopause marks the edge of the sun's influence. As the solar wind flows outward from the sun, it eventually meets the interstellar medium, the rarefied gas and dust between stars. This boundary is called the heliopause, and it defines the outer edge of the sun's protective bubble, the heliosphere. Beyond this point, the pressure from other stars and galactic particles becomes stronger than the solar wind. Voyager 1 crossed the heliopause in 2012, followed by Voyager 2 in 2018, entering true interstellar space. Though the sun's gravity stretches much farther, the heliopause marks the end of its energetic reach, the last breath of solar influence before the depths of space begin. The solar system drifts through the local cloud. Our entire system moves through a region of space called the local interstellar cloud, a thin concentration of gas and dust about 30 light-years wide. It's part of a larger structure known as the local bubble, formed by ancient supernova explosions. As the sun travels through this cloud at about 7,000 kilometers per hour, its heliosphere acts as a shield, deflecting interstellar material. Scientists study this cloud to understand how interstellar conditions might affect cosmic rays, heliosphere shape, and even Earth's climate. We're not standing still in space. We're slowly and silently sailing through galactic fog. The solar system's edge isn't defined by gravity. The sun's gravitational pull extends far beyond Pluto, holding distant comets and icy objects in the Oort cloud. But when scientists talk about the edge of the solar system, they often mean the boundary of the heliosphere, the region where the solar wind meets the interstellar medium. This edge, called the heliopause, marks the point where the sun's magnetic field and particle flow influence ends. Gravity reaches farther, but the energetic border is where space between stars begins. It's a subtle, shifting boundary, more a change in pressure than presence. Planetary atmospheres slowly leak into space. Even dense atmospheres like Earth's aren't eternal. Over time, light gases like hydrogen and helium can overcome a planet's gravity and escape into space. This process, known as atmospheric loss, is more pronounced on smaller planets with weaker gravity, such as Mars and Mercury. On Venus, the absence of a magnetic shield allowed solar wind to erode part of the upper atmosphere. Earth loses thousands of tons of hydrogen each year. Though easily replenished, the slow escape of gases is a quiet leak into the void, a constant exchange between planets and vacuum. Some moons may have formed from ring systems. Just as ring systems can decay or vanish over time, they're also capable of birthing moons. In Saturn's case, it's possible some of its small outer moons first clumped together from ring material that condensed beyond the Roche limit, the threshold beyond which gravity allows material to gather into moons instead of tearing it apart. Moons like Pan and Daphnis, orbiting within Saturn's rings, may still be building themselves from them. These moonlets serve as quiet sculptors of the rings. Their gravity carves gaps and waves in the icy hoops around them. Voyager 1 still sends data from interstellar space. Over 45 years after launch, Voyager 1 continues transmitting faint signals to Earth, traveling the interstellar medium billions of kilometers from home. Its instruments measure cosmic rays, magnetic fields, and plasma density in the space between stars. Power is limited, and systems are gradually being shut down to preserve resources, but the probe still functions. It uses a small nuclear power source and communicates through the deep space network. Each signal takes over 20 hours to reach Earth. a whisper from the edge of human exploration. The solar system completes a galactic orbit in roughly 225 million years. While planets orbit the Sun itself also moves, orbiting the center of the Milky Way galaxy. It takes approximately 225 to 250 million years for one orbit, a journey sometimes called a cosmic year. During this time, the solar system drifts through different regions of interstellar space, potentially passing through spiral arms, star-forming regions, and clouds of gas and dust. This motion may affect comet activity and, over longer timescales, even Earth's climate. We're not fixed in space. We're part of a vast, slow spiral, riding the galaxy's carousel. And so our quiet journey through the solar system comes to a gentle close. From the inner world scorched by sunlight to icy moons whispering in darkness, we've wandered together through orbits, storms, and shadows, one peaceful fact at a time. If your eyes are growing heavy now, that's wonderful. Let the last traces of starlight fade behind your thoughts, and let your breath gently carry you to rest. There's still so much ahead to discover, but for now, you've learned enough. You've traveled far, and the universe can wait until morning. Thank you for spending this time with me. And so, beneath the quiet stars, the story continues. I hope you sleep well and have peaceful dreams. Good night.